I'm starting the class. Please share that yesterday's task so that I will see and I will just I'll check that. Okay. Okay. Today we'll discuss about this silicon wafer and CZ method, masking and photolithography. So silicon wafer, how we are creating the silicon wafer, I will tell you. Okay. So how we are creating silicon wafer means first, yeah. So first silicon. So that means why we are preferring silicon? Anyone having the idea why we are preferring silicon in the the semiconductor? Why not germanium? Why we are preferring silicon? Why not germanium? In the semiconductor physics, I started means I told you know that like germanium, it is unstable with the temperature and so 100 degrees Celsius it is unstable. Yes, yes, yeah. So it is abundantly available. One reason is silicon is abundantly available. Around 28% of earth crust is available for the silicon. Okay. So why silicon? Why silicon means here most of the earth crust consists of silicon. So normally it is available in the seashores and all those things. Silicon dioxide is nothing but it is available in terms of silicon mainly it will combine with the glass, sorry, oxide. Okay, oxygen. It will combine with the say oxygen. And it's basically it's a hard material that is a glass. Okay. So here that means silicon when silicon combined with oxygen and a high temperature to form a silicon dioxide. Okay, yes, silicon plus oxygen will give silicon dioxide. Okay, silicon dioxide. So refining of silicon, if you see there are yeah. Oh, sorry. That is finished only. We are seeing the means different methods of refining the silicon. That I told you now. Two methods are there, like uh, twin tube and N-well method. Okay, yeah. If I tell you, means if I tell you that, you will get some idea that fabrication and what methods we are using. So we are discussing each and every method in detail. Yeah. Okay. Understood. Yeah, yeah. So basically, uh, we will refine the silicon by using two methods. One is metallurgical graded silicon. Refining of silicon. There are two steps are there. What are those means? One is electrical metallurgical graded silicon, and next one is electronic graded silicon. So metallurgical graded silicon means here what you are doing means silicon. So silicon is available in terms of oxygen. No? So that is silicon dioxide. So in the metallurgical graded silicon, what you are doing means you are reacting the silicon dioxide with carbon to form a charcoal. Okay, so charcoal you are heating this one with a temperature of 1500 to 2000 degrees Celsius in the electronic furnace. Okay, in the electronic furnace you are heating this. Okay, so silicon dioxide is reacted with the carbon. You are getting silicon plus carbon dioxide is anyway gas. This will be liberated. Okay, so silicon is reacted with carbon. Around you are heating at 1500 to 2000 degrees Celsius and so you are getting silicon plus carbon dioxide. Okay. So silicon and carbon dioxide. So resulting in that is this silicon. Okay. This silicon is nothing but we call as uh, uh, metallurgical graded silicon. This is the silicon we are getting nothing but metallurgical graded silicon. So this is mainly we are not using for the semiconductor. Mostly this is used for the metallurgical industry like iron industry or steel industry. That 98% of pure silicon we are getting, but we are not using for the semiconductor. Mainly we are using for a metallurgical industry. The silicon we are using in the metallurgical industry like ferrosilicon. Okay, we can manufacture ferrosilicon and like that. Okay, so this is like the silicon, silicanes, aluminum alloys, solar, and others. All those things are. So that metallurgical graded silicon is the byproduct in the electronic graded silicon. Whatever the 98% of silicon you are getting, no? So 98% of silicon you are using you are using, and that we are using as a byproduct in the electronic graded silicon. The electronic graded silicon in what you are doing means, we are taking the powdered metallurgical graded silicon that we are making to react with the hydrochloric acid at 300 degrees Celsius, okay, in fluidized bed reactors to form silicon hydrogen chloride plus hydrogen. Silicon hydrogen, when silicon is react with the hydrogen chloride, we are getting silicon hydrogen chloride with hydrogen you are getting. Okay. Uh, so uh, uh, here what happens means, so these are available in terms of halides. Silicon hydrogen chloride is available in terms of what? Halides. Hydrogen is nothing but one halide. Okay. So this silicon hydrogen chloride is having low boiling point. Low boiling point. How much of boiling point? 31.8 degrees Celsius. Okay. Through the distillation process, we can remove these halides from the. We can remove halides from the silicon hydrogen chloride. We can remove the halides from the silicon hydrogen chloride. Okay. So how to do the distillation process? That means we need to react the silicon hydrogen chloride with hydrogen. So we need to do with 1100 degrees Celsius for we need to do with 200 to 300 hours to produce form a pure silicon. Okay, so 200 to 300 hours means we are making for around 13 days. I think 200 to 300 hours means we are making for 13 days. So that pure silicon is formed. Pure silicon is formed. So this is the pure silicon we are getting. We are using in the semiconductor industry. So did you understood what are the process happening? Did you understood? Shall I move forward? So why silicon means silicon is abundantly available. So silicon is available in terms of when it is react with oxygen, it is available with the silicon dioxide. First refining of silicon means first we need to remove the oxygen from the silicon, that we are doing in the metallurgical graded silicon. How we are removing means in metallurgical graded silicon we are reacting this with carbon. So that means carbon will be added with oxygen, carbon dioxide anyway gas is there. Silicon is silicon you are getting. So this is 98% of silicon. This is available in the metallurgical grade silicon that we are not using for the semiconductor industry. Okay, 98 that consists of 98% of pure silicon. Okay, this we are using in the metallurgical industry. Okay, that is taking as a byproduct in electronic graded silicon, and we are reacting this with the hydrochloric anhydrous. Anhydrous. We are reacting this with the anhydrous hydrochloric acid. Normally, hydrochloric acid is available in terms of liquid. No, this will be available in terms of liquid. So anhydrous means what? It is in terms of powdered form. It is in terms of what? Powdered form. Okay, anhydrous means what? Without any water. Without any water. Okay, this is available in terms of powdered form. So this is fluidized in bed reactor to form a silicon hydrogen chloride, and this is having a low boiling point. So that means that we can do the distillation at 31.8 degrees Celsius. So we are reacting the silicon hydrogen chloride with hydrogen, and at distillation process is done at 1100 degrees Celsius. So we need to do with the 200 to 300 hours to produce a pure silicon. This we are using for the semiconductor industry. Did you understood how I am purifying the silicon? Your response? Any doubts or queries? Yeah, yeah. So, so that is a silicon wafer. So that means why silicon? Okay, silicon is abundantly available. Okay, silicon is 1 minute.
ఇక్కడ పెట్టాలా
అదే
తింటావా ఇవి హర్ష చిప్స్ తో చేసినాయి ఆనియన్స్ దాంట్లో పిండిలో వేసి హర్ష చిప్స్ కాన్షియేషన్
సరే అక్కడ పెట్టుకుంటా. So why silicon? Silicon as a material you are using abundantly available. Around 25.7 degrees F rest is available. Okay. availability of simple techniques to refine the silicon, availability to simple techniques to grow the single crystal, and ideal properties of silicon and silicon dioxide. Okay, so in the MOSFET, you are using what we call, we are using silicon dioxide, no? Okay, to make this silicon dioxide, other material is not required. Just silicon, we are reacting with oxygen. You are getting silicon dioxide that we can use as insulator, that is oxide material insulator. Okay, and invention manufacturing technology is based on the planar process. Okay, so this is the why silicon as a material. Okay. Mm, Mostly the silicon structure, if you see, silicon structure, I will show you. This I took from the plumber and graphene. Okay, this is the copyrights of plumber and graphene. And if you see the plumber and graphene book, I think in the 64th page, I think so, crystal structure. So mostly the crystal structure will be, this is a unit cell. Normally, this is a unit cell. Okay, unit cell of what simple cubic structure. So unit cell will be like cubic. Cubic means what? How many sites are there? Atoms will be available in terms of 8 sites are available. Okay, 8 sites. Yeah, these 4 sites, 4 sites. Okay, this is nothing but cubic structure. BCC is nothing but centered cubic structure. Centered cubic structure means here 4 sides, that 4 atoms will be there, and at the center one more atom is there. This is nothing but BCC. BCC is nothing but body centered cubic structure. Okay, so normal cubic structure, BCC is nothing but body centered cubic structure. See here, the body centered cubic structure has extra atom in the center of the cube. Okay, and one more structure is face centered cubic structure. This is nothing but face centered cubic structure. Face centered cubic structure means what? Face centered cubic structure means here, this is face centered cubic structure has extra atom in center of each faces of the cube. So that means here, corners you have four atoms, and each faces you have atoms. Okay, you can analyze the three-dimensional view. So top view, top and bottom, two atoms. Okay, and sides, two atoms, like that. So total, how many sides are there? Two, four, 6 sides and center. You have different atoms. That is nothing but face-centered cubic. Did you understood the cubic structure and body-centered cubic structure and face-centered cubic structure? Shall I move forward? Hello. So this is body's cubic structure, and this is the center atom will be there, and this face-centered cubic structure means at all sides one more atom will be there. Okay, like if you see, for example, atom A is in cubic structure to atom B, that move in a direction. How it is moving means in the direction of this three-dimensional view. This is X, Y, and Z. Okay, X, Y, Z. Then one direction is the crystal. So normally one direction is the crystal. Okay. Suppose atom A to atom C means what? Atom A to atom C means 0, 1, 0 is the direction. When it is moving from atom A to atom, all direction means 1, 1, 1 direction. Atom A to atom C means what direction? 0, 1, 0 direction. Okay. Many directions are there. Basically, we are concentrating on these two directions. Okay. So how the crystal structure will be there means, that's crystal structure of silicon. Okay, structure of silicon. Okay, silicon is a diamond cubic structure. Diamond cubic structure. This structure is what? The structure is visualized as two merged FCCs with origin as a second lattice offset from first lattice A by 4 by 3 directions. See here. So this is my FCC, face centered cubic structure. This is my FCC. Okay, and here two merged FCCs. Okay, two merged FCCs like this. This is the silicon structure. Did you understood how the structure will be there? Two FCCs merged together. Okay, this is a diamond structured structure of silicon. That is, unit cell may be two merged FCC cells. What is the offset from each other? What is the distance from three directions? A by 4. A by 4. Between the two directions, what is the distance from this atom to this atom? The distance is A by 4. Distance is A by 4. So this is the crystal structure. Okay. So crystal structure means you have like face-centered cubic structures merged together. It is visualized as two FCCs merged together. Okay. Two lattice, two structures of FCCs merged together, and the distance between two each and every like first lattice and second lattice is how much is in the three directions A by 4. Did you understood the structure of silicon structure? Silicon structure. Did you understood? Shall I move forward? Waiting for your response so that I will move forward. Hello. What about others? Shall I explain one more time? You understood, no? Okay. So first is what a cubic structure. Okay. So you can go through this. I think I shared in the Google form, Google Drive, that plumber book. You can go through that and you can see in the from the 64th page. I think from 65th page. So this is the cubic structure. This is body-centered cubic structure, and this is face-centered cubic structure. How to visualize the silicon structure means two two FCCs merged together, and the distance between two lattices, first lattice and from the origin, okay, with the origin of second lattice is how much means A by 4. Okay, okay. I'm going through the PPT. Hope you understood. Next, see here. So how the silicon structure will be there? There are two principal silicon orientations are there. I told you, 111 and 100. These are the two planes are available. So mostly this 111 we are not using. Why? Because this plane will oxidize as faster. This plane will oxidize as faster. So because of these electrical properties, mainly we will use this 100 interface. Okay. So how the silicon structure will be visualized? It's a diamond cubic lattice structure. It is visualized as two FCC lattice. Okay. So if I directly tell you, you can't understand. That's why from the textbook I took this FCC structures, two FCCs merged together. Okay, and origin of second lattice offset from the first lattice is how much? A by 4 in all three directions. In all three directions. Okay, several types of defects are there. You can go through that plumber book. Okay, point, line, area, volume. Okay, these are the commonly found in the crystal. Um, these defects play the important role in the silicon technology. Okay, this is about the silicon structure. Do you understood the structure of the silicon? How it will look like, how it will visualize. Shall I move forward? Okay. Okay. So refining of silicon, if you see, so first what you need to do, so refining of silicon, there are two methods are there. One is metallurgical. First method is nothing but you need to do MG, metallurgical graded silicon, and next electronic graded silicon. So metallurgical graded silicon, so silicons are mainly available in terms of what? Quartzolite. Quartzolite is nothing but chemically silicon dioxide. Okay, that is one type of sand only. That is one type of sand only. So that steps I told you, chemical reactions. So metallurgical graded silicon, you are getting 98% of pure silicon. And next step is you need to do in the electronic graded silicon. In electronic graded silicon, you have purified form of purified form of silicon is available in the electronic graded silicon. This is the refining of silicon. Okay. So after that, you need to grow the like you need to grow pure silicon. Okay, so for that pure silicon, you will go with the one method that is nothing but the Czochralski process. The Czochralski process, or we can call a CZ process. The Czochralski process, or we can call this as CZ process. Okay, this is the method to crystal growth is used to obtain the single crystal silicon. So in order to get the single crystal silicon, we are going with what CZ method. Okay, CZ method means what? Mainly we are using the CZ method for semiconductors, like to grow silicon, single crystal germanium, or single crystal gallium arsenide. And the metals also we are using, like palladium, platinum, silver, gold, or in salts also we are using the CZ method. Okay. Uh, so in CZ method, so what is the CZ method? So this is highly refined electronic graded silicon. So I told you, know, in electronic graded silicon, you are getting like 100% silicon, but still it is polycrystalline. Polycrystalline means what? Some impurities are there. Some impurities are there in the whatever the byproduct of electronic grade silicon. Okay, so in order to make as a single crystalline silicon, okay, silicon, in order to make impurity free, we need to uh, we need to process to become a single crystal. So how you are processing means you are going with CZ method or Czochralski crystal growth process, Czochralski crystal growth process, to produce in the single crystal ingots. Ingots. Okay. Ingots means I will tell you. Suppose ingots means suppose if you take pencil, okay, a pencil. So that means when you are sharpening two sides, how it will look like? This is ingot. Like two cones, two sides, and one cylinder. This is nothing but ingot. We'll discuss. Okay, don't worry. We'll discuss what are these ingots. So through the CZ method, you are getting the single crystalline silicon ingots. You are getting ingots. Okay, remember ingots. Okay, CZ method, and this is basically my CZ method. So CZ method basically it consists of mainly four parts are there. One is uh, uh, one is control system, and next one is a rotating mechanism. Okay, mechanism, and next one is ambient control, ambient control, and next rotating shaft. Okay. So here, if you see, this is a like what you are doing means this is a simple method only. So if you understand, this is simple only. Here you have like this is nothing but crucible, and in the crucible there are some heaters are there. Okay, in the this one you are heating. Okay, this is nothing but molten silicon in molten state. Silicon in molten state. Molten state means in liquid state, the silicon will be there, and there is a shaft. Okay, there is a seed shaft. In the seed, this is nothing but this is seed crystal, seed silicon. In the seed silicon, what you are doing means with the help of this uh, here there is a choke. Choke means Suppose here this is the shaft. This is nothing but one choke. It is means uh, uh, it's means choke is used to means tie this silicon seed silicon. Okay, choke is used to tie this seed silicon. Okay, so mostly you are using seed silicon. Seed silicon means pure silicon, and that is in form of seed. So normally it's a small seed crystalline silicon. Okay, so normally what you are doing means here uh, uh, sensor control also there. Okay, so normally what you are doing means this crucible and this rotating shaft, you are moving in anti-clockwise direction. Okay, whatever the seed shaft rotating, and so parallelly, and this crucible, whatever this crucible is there, both are like so crucible is rotating is there. So this is rotating crucible. Okay, So both are rotating in opposite direction. That means suppose seed shaft is there, seed shaft is rotating in clockwise direction. This crucible is rotating in anti-clockwise direction. Okay. So slowly, what you are doing, the seed shaft, you are dipping in this molten silicon. Okay. So slowly, you are dipping that seed crystalline along with the shaft, and slowly you are moving and rotating in opposite direction. Either the seed shaft is rotating in clockwise direction, and this crucible is rotating in the anti-clockwise. So it is clockwise direction, anti-clockwise direction. So what happens? Whatever the molten silicon is there, that will be stick to the shaft. Okay, that means the amount of diameter it is sticking to the shaft depends on how much of how much of slowly you are dipping into this molten silicon, and you are taking out. Suppose in the fast manner you are dipping and taking, means you are getting less diameter. In slow manner you are dipping and taking out, means you are getting the more diameter of the silicon. Okay, and basically so this is molten silicon. It can contaminate with the other gases. Okay, other gases. So in order to overcome that contamination, you need to make ambient gas inlet. Ambient gas inlet means you are passing some inert gases, like argon gas, like inert gases. This is nothing but ambient inlet. So in order to overcome that contamination, okay, molten silicon may react with some other oxygen, or it may form hard material like silicon dioxide, or it may react with some gases present in the atmosphere. So in order to prevent that, we are using this ambient control. Ambient control. Okay. This is the basic. So there is a control system, and power supply is also there. So power supply is given to this crucible, and heaters are there. Okay, heaters are used to heat this furnace. Okay, and some vacuum pump also there. Okay, and this is nothing but CZ method. Do you understood this method, this technique? Any doubts or queries? Okay. Yeah, see that. Just you can Google it. Okay. You can Google it. See that. See that. This is simple technique only. Okay. This is simple technique only. Just see that method. See that method diagram. Okay. See that method diagram. Images. Mm, yeah. This is the Czochralski method. Okay. So you can see here. So this is the Czochralski method, and inside this is a seed crystal, and crystal melt in molten state. Okay, molten state. Slowly there will be equipment inside, slowly rotating the crucible, and slowly rotating this shaft, and slowly you are moving, and all those things like that. Okay, you can see and you can understand what is this CZ method and all those things. Did you understood this? Shall I move forward? Any doubts? Shall I explain one more time, or shall I move forward? Waiting for your response. Hello. Oh, okay. Okay. Yeah. So that means, see here, a pieces of electronic graded are placed in silica crucible along with small amount of doped silicon. Suppose here pure silicon is there. Suppose if you want n-type semiconductor, what do you need to do? Here you need to add some more donor atoms. What are the donor atoms? Like phosphorus, arsenic, antimony, bismuth. Okay, so if you add some more amount of phosphorus, you'll get n-type material. Suppose if you want p-type material. Okay, if you want p-type material, means trivalent impurities. This is pentavalent impurities. Trivalent impurities are nothing but suppose if you are adding boron in this, you'll get so that means when you are dipping and slowly moving, you are getting p-type material. Like this also, you can make n-type and p-type material. That we can can combine and we can make this PN junction diode, and we can use in the MOSFET and all those things we can use. Okay, so like this also uh, we can make a P type and N type material. Okay, uh, so the melt temperature is stabilized at silicon melting point. This is the silicon melting point. What is the silicon melting point? 1417 degrees Celsius. So that means this is in molten state now. This is in molten state. We need to stabilize the silicon at a silicon melting point, that is 1417 degrees Celsius. Okay. Small crystal rod of silicon called seed crystal. Seed crystal that is lowered into the melt. Load into the melt. Slowly, you need to dip in the molten silicon. Okay. After dipping the molten silicon, crystal orientation of the seed will determine the orientation of resulting pulling the crystal and wafer. Okay. You need to slowly, whatever the furnace is there, rotating in anti-clockwise direction, and the seed shaft is rotating in clockwise direction. Slowly it is rotating and it is dipping on the molten crystal, and slowly you are taking out. Okay, you are taking out. Okay, that is same the method. Okay, so what happens? Monolithic IC usually fabricated on substrate which is doped with impurities. As I told you, no. So when you want to do N type and P type materials, we need to dope with the impurities in the molten the silicon. Okay, dopants are placed. Whatever the dopants, like suppose if it is N type silicon, we need to dope with the dopants. What are the dopants? Phosphorus atom. So if you want P type material, you need to dope with the boron atom. Okay, crucible with silicon will determine the doping concentration in the resulting crystal. Okay, so seed is slowly pulled out of the melt. Okay, silicon atom from the melt bond to the atom in the seed. Lattice planes the lattice forming a single crystal seed crucible upward. Okay, how much diameter is the resulting crystal is controlled by primary rate of which crystal is pulled. Okay, if you pull faster pulling results in smaller diameter. For slower pulling results in slower diameter. Okay. So conditions of crystal pulling are therefore carefully controlled. Okay, if you want more diameter, slowly that should be rotated in opposite direction, clockwise and anti-clockwise. Slowly you need to take out. Okay, you need to take out so that you will get the large diameter. Okay. Uh, so as I told you, know, seed and crucible are normally rotated in opposite direction. Okay, so if it is rotated in clockwise direction, seed means rotating shaft is rotated in clockwise direction. Crucible should be rotated in. So this should be rotated in anti-clockwise direction, and this seed rotating should be clockwise direction. Both should be rotated in opposite direction. So this promotes the uniform growth. Okay. So dominant choice of crucible material is mainly quartz. Okay, relatively that is that is in molten silicon. So crystal growth is normally performed in argon ambient. As I told you, no. So why you are using argon ambient? Here you see here ambient gas inlet is there, no. So mainly you are using argon. So why you are using argon? Argon. Why you are to avoid the additional impurities from the ambient, in order to overcome that additional impurities added into the molten silicon. So we are using the ambient control. Okay. So this is the mainly the Caesar method. Okay. Hmm. After a crystal growth is in the CZ method, there are some series of mechanical steps we need to do. Shaping and growing the crystal to uniform diameter. Okay. And we need to say you are getting ingots. You are getting ingots. Okay. So these ingots you don't want. You need to cut this edges. Okay. And sawing into individual wafer, mechanical lapping operation, and chemical etching. Etching means unwanted things we need to remove. Polished under pressure and wafer identification. These we need to do. Okay. These are nothing but ingots. Have we understood what are ingots? After taking out, you are getting a like ingots. These are nothing but we call as ingots. Ingots. Okay. So ingots, you need to do these steps. That means these edges you need to cut, and you need to make what we call in terms of die. Die means what? Die means it's like a CD type. So it's a CD like we can look like it's a papad like or CD like crystal. Like this, it will be available. Okay. So what are the physical properties? That means diameter, thickness, blackness, mechanical defects, crystallographic defects. These are the physical properties. Electrical properties means either it is N type or P type, or dopants or resistivity. These are electrical properties. Impurity levels means either it may be oxygen or carbon. This is nothing but my dye, silicon dye. Okay, silicon. So see here, a diaper wafer if you take, typically diaper wafer is it can be 16 inches or 150 nanometer. Okay, and 8 inches or 200 nanometer or 12 inches or 300 nanometer. So this is the thickness. Okay, as the number of peripherals are increasing day by day, what happens, dice are also increasing. Okay, so mainly we can use 12 inch, that is 300 nanometer die size we are using. Okay, die per wafer. So suppose if your total die is a 300 nanometer, so so that means 3.14. So what is the area of circle? Diameter is 150 nanometer, 3.14 into 150 into 150. So you are getting 70696 millimeter square. Okay. So consider one typical size of chip to be maximum 1 millimeter into 1 millimeter. So so 70,000 die should be accommodated in 300 nanometer wafer, considering die will be not fully patterned across the edges. Okay. So commercial CPUs are available in terms of 20 cross 20, that is 400 mm. So in this you are making the CPUs within this die, within this die. Okay, you are making the CPUs. Okay, so that means we can make 148 CPUs for 300 nanometer wafer. 300 within the 300 nanometer wafer we can make 148 CPUs. Okay, so this is the die. And photolithography means yesterday I told you how to do. You will need to do like photolithography is process whatever the unwanted material that we need to remove, and what are the material we want that we need to keep. Okay, that is lithography. There are major processes are there: lithography, etching, deposition, and doping. Okay, these are the process we have in the photolithography. Okay. So this is pattern mask. So we need to mask whatever the material we want, and whatever the material, whatever the uh, means shapes we don't want, we need to do. We need to evaporate, means we need to do with UV rays or chemical process. That is photolithographic process. Okay, three steps are there like coat, expose, or develop. These are the three steps we need to use in the photolithography. Okay, coat surface condition, coat spin coating, coat photoresist, coat soft bake, all these things are developed in the photolithography. So this is about the development of the silicon wafer. Any doubts or queries in this today's session?